Good afternoon, everyone. Okay, so welcome to our first tutorial. Okay, yeah, actually, it is still online, but who knows? Maybe halfway we might change to physical. We might get some classrooms. Okay, yeah. So in the past, it always used to be in a classroom, one or tutorial classes. Okay, but ever since COVID, it became online, and I think we're still continuing this way for a while. All right. So just take note of the schedule every time. All right. Whenever your tutorial will be online. All right. So don't come to the studio. Okay. If you happen to come to school, then yeah, you can still hang around. Maybe go makers or somewhere. And then yeah, take the tutorial class. Okay. So just a few things. So far, I think the classes are progressing well. So like we said in the beginning, the idea of EBP module keyboard 1 and 2, right, is not the traditional sense, correct? So one of the common feedback, okay, that we get from students is that the lecture material is too brief, it's too little information. I don't have enough practice, and I'm not very sure what is actually happening in the studio and so on. All right. So the direction of the module is structured to be in that sense. All right. We do not want to overload you with so much of lecture and theory in the front end. So we give you bite-sized information, and the idea of the studio is for you to get some understanding from the experiments and the observations. Okay, so that is the intention. All right, and we hope that when we do the tutorial questions and all these additional practice questions, those concepts reinforce and you are better. Okay. Yeah, so I mean, I think that's usually one of the common feedback we get from students. I just want to again, hopefully, make you understand the rationale behind this module. I think every other module that you take, it is mostly traditional sense. Right? That means you usually have an hour or 2 hour lecture class plus some lab and tutorial. All right. So this module, EVP module, is designed to be different. All right, because of the experiential learning that we want you to have. Okay. Yeah. So let's so before we head on with the tutorial, I think those of you who attended the CG briefing, okay, I shared some projects, and I talked a bit about entrepreneurship and some options that you have. So I just want to share another thing that our students have done in the past, CG students. Okay, so let me bring up this. Okay, so this is this website. This actually, as I put in the chat, it is actually a coding platform created by our CG students. Okay, so it was, I think most of you know Scratch programming and something similar sort of tools where we get kids to code by having some block-based coding. All right, so our students, they brought it up one level higher. Correct, they incorporated some 3D elements, some gaming concept, okay, into that, and they created a platform, and they got funding. Okay, and it was going on quite well. So again, if you look at the team over here, they're all CG students and all have graduated. So I do not know whether this is still something they're working on or they just left it. All right, but all these are CG students who have just graduated. Okay, so this main guy Rishi, so he is now in the US. He just messaged me the other day. Okay, so he moved to a startup in the US. So I'm not sure about the rest. Okay. So again, when you have an idea, you want to work on it. All right. Within SOC, they have options. Okay. If you look at the NUS level, okay, there's this NUS Enterprise. Okay. So this gives you a lot of other sort of avenues where you can look at how to get funding, or maybe not even funding, but maybe space, to work, to resources, and so on. Okay, so like I said, there is no nothing to limit you. Okay, I'm sure all of you are already receiving updates from the Makers Lab, all right, on workshops that we conduct. Okay, so please make use of that when you have the time. And if you want to work on anything, go ahead. If you have an idea, you can ask for funding. You might get it, you might not get it, but it's always good to try. Correct? Okay, so again, these are just things I wanted to bring up for you all to have a look when you all are free. Okay, so let's go on to start our tutorial. Okay, so while I'm going through the tutorial, if you have any questions, you can unmute and ask, or you can put in the chat as well. Okay, and then we will discuss. Okay, so the slides, I will not go through all the slides the first half, because all of them are the concepts already covered. Okay, so I don't want to bore you and go through all the same concepts again. Okay, I think we have already sort of have some basic understanding of these concepts through whatever we have done in the studio so far. Okay, so let's go on to the questions proper. Okay, so let's look at the first question. So the first question, we have a battery. Okay, so this battery is having an internal voltage of 12 volts. Okay, so this is 12 volts here. Okay, and internal resistance R1 of 0.15 ohm. Okay, so find the load current and the corresponding power for the load if your RL is 10 ohm. Okay, so if my RL is 10 ohm, my load current will be V over the total resistance. In this case, it will be 12 over 0.15 plus 10. Correct, that will give me 1.18 ampere. Okay, and they also ask you to calculate the efficiency. So the efficiency is basically power, that means what is useful power over the total power provided by the system. So in our case, the useful power is always the power that is delivered to the load. That means what is consumed by the load RL. Okay, so the efficiency can be computed as I square RL, that means the power consumed by the load, over the total power provided by the battery. Okay, so that will give me 1.18 square 10 over 12 and 1.18. So that will give me an efficiency of 98.5%. All right, so I think this is quite straightforward. Okay, so let's the same question, but now we are having a load resistance of 1 ohm. Okay, so the calculations will still be the same. Okay, calculations will be the same. So the current will be 12 over 1 plus 0.15, which should be 10.4 ampere. And the efficiency will be 10.4 square multiplied by 1, 12, and 10.4, which will give me 87%. Okay, so from this you can see that, you know, when your current is high, so if you could just compare the current, okay, when the current is high, okay, what happens? You lose a lot of sort of power is wasted, okay, within the internal resistance of the battery itself. All right, so the efficiency drops. All right, whereas if your current is low, okay, then a greater amount of the generator power is transferred to the load. All right, so again, that is sort of one of the takeaways you can get from this question. Okay, so that is why when you have a battery connected to a load, okay, if the load draws a lot of current, the efficiency will be very low. All right, whereas when the current is lower, the efficiency gets higher. Okay. Okay, so question 1, I think it's just some basic introduction. Okay, just to recap the Ohm's law and efficiency. Okay, those concepts. All right, so I think there is nothing much to discuss there. Okay, question 2. Question 2 is to find the voltage difference or the voltage across AB. Okay, so the first thing is when you see the circuit, okay, we can simplify the circuit. So we know that 100 and 150 ohms are parallel, correct? Okay, so if you're still confused, okay, you always look at whether there is a sort of branch in the current. Okay, so when the current comes here, we know that at this point it will split. So as long as the current splits between two or more branches, then those branches are considered parallel. Okay, so in this case, since I split into 100, 150, this is equivalent to me drawing it as 10 volts, okay, 100 ohm, and this, okay, which will be 100 parallel 150, which is equals to 60 ohms. Okay, so now this voltage here, okay, is basically a voltage divider. All right, that means it is basically 60 over 60 plus 100 multiplied by 10 should give me 3.75 volt. Okay, so since both 100 and 150 are parallel, the same 3.75 volts is across the 100 ohm and across the 150 ohm. Okay, they are both parallel. So VAB will be 3.75 volts. Okay, so I will just proceed. Okay, like I said, if you have anything that you're not sure, okay, just feel free to ask. Okay, then I will explain further. Okay, question 3. Question 3 is again revising our KVL and KCL concepts. Okay, so basically what we can do is we can sort of write out some expressions based on the polarity already given to us. Okay, so in our case, we have a circuit where the directions of the currents are already given and the voltage drop across the components is, or the direction of the voltage drop is also given. So we follow that, okay, when we are coming out with the expressions. Okay, if nothing is given, then we are free to make our own assumptions and come up with our KVL and KCL expressions. Okay, but in our case, it is already given, so we have to follow based on what is given. Okay, so if I look at the loop on the left, okay, if I draw a loop over here, okay, so we can see that, okay, if I look at all the voltage drops over here, for V1, the plus is on top, minus is below. Here, the plus is here, the minus is here. So when I do a clockwise loop over here, the V1 and the voltage across R3, VR3 are both in the same direction. All right. Whereas the voltage drop across VR1 and VR2 are in the opposite direction of the loop that I've drawn. Okay, they are in the opposite direction of the loop that I've drawn. So by KVL principle, okay, when you draw a loop, all those in the same direction, okay, voltage drops will be equals to all the voltage drops in the opposite direction. Okay, so you can formulate an expression to say that V1 plus VR3 is equals to VR1 plus VR2. Okay, again, why we have this expression is because we have drawn the loop this way. All right, and all those in the same direction as our loop would be on one side, and all those on the opposite direction of the loop would be on the other side. All right, so with this, if I rearrange it, V1 plus VR3 minus VR1 minus VR2 equals to 0. So that is the expression over here. Okay, so that is a valid expression. Okay, similarly, I can do the same thing on the right hand side. So I can draw another loop. So it doesn't matter which way you draw. You can draw clockwise or anti-clockwise. It will follow the same concept. So if I were to draw anti-clockwise here, it is the same thing. That means I say that V2 and VR4 are in the same direction as my loop. Okay, whereas VR2 and VR5 are in the opposite direction of my loop. Okay, so if I look at the right hand side of the circuit, when I write the expression, it's the same thing. Whatever is along with my loop direction, that means V2 plus VR4 is the same as all those in the opposite direction, which is VR2 plus VR5. Okay, which means that if I rearrange this, VR4 minus VR2 minus VR5 equals to 0. And that is this expression here. Okay, it is this. Okay, in terms of current, okay, we just follow what is given. So we can say that if I look at this branch over here, okay, this point over here, I can say that whatever current flowing in, which is IR1, is equivalent to the current flowing out, which is IR2 and IR4. So I can say that IR1 is equals to IR2 plus IR4. Okay, and if I rearrange that, I will get IR1 minus IR2 minus IR4 equals to 0. Okay, and that is your expression over here. If I look at this branch, so this entire branch, this V1 branch over here, IR1 is the same as IR3, correct, in terms of magnitude. But you can see that current can eventually only flow in one direction, correct? Current can only flow in one direction. That means IR1 and IR3 are actually opposite to each other. Okay, so IR1 and IR3 are actually opposite to each other. So you can say that IR1 equals to negative IR3. Why? Because both IR1 and IR3 are actually the same current, because in the same branch. Alright, but if you look at both their arrows, they are both pointing in opposite direction. Okay, so in terms of magnitude, they are the same, but direction, they are opposite to each other. Okay, so if I rearrange, I'll get IR1 plus IR3 equals to 0. Okay, so that is this expression here. And the same thing applies to IR4 and IR5. Both IR4 and IR5 are both again on the same branch, which means that they have the same magnitude, but they are in the opposite direction. So the same thing. So you can say that IR4 is actually equals to negative of IR5. So again, IR4 plus IR5 will be equals to 0. Okay, so that is this, and that is this expression here. Okay, so that is how you can come up with all the expressions. Again, this is based on the convention of the plus, minus, and directions already given to us. Okay, already given to us. Okay. Later on, again, we will look at other examples where we will define, correct? Like when we did the node analysis and so on. When nothing is given, we can decide, correct, how to label the currents. Okay, and then we come up with the equations based on our own assumption. Okay, so based on all these correct expressions, option B is the one where both the voltage expression, KVL, and the KCL are correct. Okay, so that is your question 3 over here. That's a question.
Sorry, sir. Can I have a question? So, like, can I ask, like, is the battery like absorbing or delivering power in this case?
Okay, in this case, we do not know yet because they haven't solved for the actual values, correct? So in this case, what we have is expressions, all right? We will only know if it's absorbing or supplying after we know the actual value. Okay, so by definition, if the current is flowing for a voltage source, okay, for any device, if the current is flowing out of the positive terminal, then it is providing power. If it's flowing into the positive source, then it's absorbing power. Okay, but that can only be known after we solve.
Okay, thank you.
Okay, so there's a question, why?
Wait, I have another question.
Yeah.
If IR1 and IR3 are the same magnitude because they're in the same branch, does it mean that IR2 is also the same magnitude?
No, IR2 is in a branch that has the influence of both IR4 or IR5, correct?
So it's considered a different branch?
Yes.
Okay, thank you.
Okay, so IR1 and IR3, there's a question, why is IR1 equals to minus IR3? Because if you look at the current, like I said, when the current that flows through the devices is the same, then we say they are series. So for series components, the current is the same. So like I said, if let's say IR1, IR3, okay, let's assume that IR1 is the correct direction. Okay, we do not know. Let's assume IR1 is the correct direction. That means whatever current that flows through resistor 3 is the same current that is going to flow through resistor 1. If it is the other direction, it's the same thing. Whatever current flows through resistor 1 is the same current that flows through resistor 3. Because there is no split anywhere along the way. So since it is the same branch, there is nothing else interfering. So these R1 and R3 are considered series, correct? They're considered series because the same current flows through them. So that is why R1 is same as IR3. Okay, the same principle for IR4 and IR5. Whatever flows through R4 has to be the same current that flows through IR5 because they are in the same branch, the same series branch. There is no point where IR4 suddenly split somewhere else before reaching IR5, before reaching R5. Okay, so as long as it is the same current flowing through the components, then we say they are series. So the series means it's the same current. Okay, so I hope that is okay now. Okay, question 4. Find the V and the voltage across the 3 ohm resistor. Okay, so in this case, you have 4 branches and you know the 4 ampere is coming in. Okay, so of course in this example it is a bit easy because all the 4 branches have the same resistance, correct? 4 ohm, 4 ohm, 4 ohm, 4 ohm. Okay, so since you have 4 branches of the same resistance, then that current that comes in will split equally into the 4 branches. Okay, if it is not the same resistance, then of course you need to do step by step, correct? You need to combine the resistance, or you need to do current divider rule, okay, step by step to figure out how much current is flowing in each branch and so on. Okay, but in this case, since it is 4 branches of the same resistance, 4 ampere will split equally into the 4. So 1 ampere, 1 ampere, 1 ampere each. All right. So if all 4 branches have 1 ampere each, okay, then what is the total voltage? Okay, so you can see that the voltage, okay, that you will get, okay, across all these branches is the same, correct? Because all these branches are considered parallel. Okay, so if I were to measure the voltage, okay, using a multimeter across all these branches, it will be V equals to IR, correct? Which should be equals to 4 volt. That is, if I measure across any of these 4 branches because they're all parallel. Plus, I also have a voltage drop across here, okay, which is 4 times 2, correct? Again, the same IR, which will be 8 volt. Okay, so effectively, the total voltage, okay, within the circuit is 8 volts plus 4 volts, okay, which will be 12 volt, which is your V. Okay, so that is the total voltage or the supply voltage, which is V. Now, how about the voltage across the 3 ohm resistor? Okay, so V is again IR, correct? So since we know that this branch current is 1 ampere, so the voltage across the 3 ohm is IR, which is 1 multiplied by 3, which will be 3 volt. Okay, so let me move on. Okay, so this question 5 is the same circuit but different values of this R, a parallel resistor. Okay, so in this case, if let's look at the first case where R is open circuit. So if R is open circuit means it is equivalent to not being there, but not being there, which means that the voltage, okay, the current through the R, the current through R will be equal to 0 because there is nothing there, open circuit. Okay, so the voltage at this point here is the same as the voltage across the 4000 ohm resistor. Okay, so it's just like if I remove the resistor and I measure the voltage across the 4000 ohm resistor, okay, that voltage will be a simple voltage divider rule. So 4000 over 4000 plus 1000 times 100 volt, which will give me 80 volts. Okay, so that is when your R is open circuit. Okay, so current is 0 and the voltage is the same as the voltage across the 4000 ohm resistor directly. Okay, if I were to go to part 2, which is the 8000 ohm. Okay, so if it's 8000 ohm, okay, then what happened? Then I need to look at the combined resistance, okay, between the 4000 and 8000. So that will give me, okay, 4000 parallel to 8000 will give me 2667. Okay, so the new circuit, okay, will be 100 volt, 1000 and 2667. Okay, so the voltage here will be equals to 2667 over 2667 plus 1000 multiplied by 100 volts. Again, that will give me 72.7 volt. Okay, and this 72.7 volts is again across both these devices the same, correct? Both the 4000 and the 8000. Okay, so to find the current here, this current I will be V by R. That means it's 72.7 over 8000, which will be 9.09 milliampere. Okay, since they are both parallel, that means the same voltage that appears in the sort of combined resistance is the same across the each individual resistance. Okay, so the same thing we're going to do for 200 ohm. Okay, so for 200 ohm, the same thing. So it will be 100 volt, 1000, and this will be 4000 parallel with 200, which will be give me 190. And if I do the same calculation for V, it will be 190 over 190 plus 1000 times 100, 16 volts. Okay, and then the current through the R here will be 16 volts over 200, which will be 80 milliampere. Okay, and then the last one here is short circuit. Okay, so whenever you have a short circuit, okay, that means, okay, let me redraw this first. Okay, and now I'm going to create a short circuit here. Okay, so we must always remember that the current by default will always take the path of least resistance. That means when the current flows, it comes to this junction over here, you will see two branches, correct? One is to the 4000 ohm and one is a short circuit path. Okay, and the current will always take the easiest path, which means that it will bypass the 4000 and all the current will only flow through the short circuit path. That means it is equivalent to saying that this becomes an open circuit. Okay, that means the circuit eventually just looks like this. It's just 100 volt with a 1000 ohm resistor, and then it's a short circuit. Okay, so always remember, whenever you create a short circuit, all the current will flow through a short circuit. Okay, that is why, for example, when we say that you measure current, correct? You must always connect in series, not in parallel, because when you connect in parallel, okay, it will create a short circuit path, okay, for current to flow, which will burn your fuse or blow your fuse. Okay, so that's the principle. The moment you create a path of very low resistance, okay, all the current will flow through that path. Okay, and then okay, the other part will be considered as open circuit. So in this case, okay, since there is effectively no voltage drop, okay, there is no component between A and B, okay, so the VAB here will be 0 because there is effectively no voltage drop across these two components. I mean, these 2 points. It's a short circuit path. Okay, so the voltage will be 0. So the current is basically this current. So this current I will be 100 over 1000, which will be 100 milliampere. All right, so that is how you look at all of this. Okay, so I mean, towards the midterm, we will come back to these concepts, okay, where you will see this thing, this concept of what you call loading. Okay, loading effect of a resistor. Okay, well, what is the loading effect of a resistor? Is, as you can see over here, the load that you connect, okay, the resistance that you connect here as a load, okay, when you connect it in parallel to another resistor, the combined resistance can have a significant effect on how much is the voltage that your load will receive and how much current will flow through it. Okay, again, these are things that if for example, okay, if I design a circuit, I say that this is my circuit and this is my 2 resistors. Okay, so you can, if this is considered open circuit load, that means nothing is connected to the load, I can come up with a voltage here, correct? 4000 over 1000, okay, say, okay, 80 volt. Okay, now, but that 80 volt will not be the same once I connect a load, correct? Because once I connect a load, the combined resistance between the load and this 4000 ohm will change, which means that the effective voltage that is seen by the load will not be the same as what you calculate without the load. All right, so again, these are things that we will come back to again, all right, when we go through some of the practice questions in a couple of weeks' time. Okay, so question 5 is, I think, just to again make you understand the effect of this additional resistor, all right, where the analysis that we do before we add and after we add can be quite different. Okay. Okay, so question 6. Question 6 asks us to find I1. Okay, so for question 6, the circuit here, okay, the way to analyze this circuit is, if you look at this line over here, this line over here, okay, there is no component here. All right, that means effectively, if you look at the way the current will flow, whatever current that flows in this part of the circuit, that means in this branch, will only be an effect of this 20 volt and this 3 ohm resistor. All right, though the whatever current flows in this branch may be a combined effect. All right, but technically this branch, I mean this right hand side of the circuit, has a current that is only dependent on 20 volt and 3 ohm, because if I draw a loop, that is all you see over here. Okay, so that allows us, okay, to split, okay, this circuit into 2 separate sort of portions. Okay, that means you can think of it as a circuit that looks something like this. Okay, another circuit over here. Okay, again, this is only because there is nothing here that is having a sort of an effect on both circuits. I mean, there's no resistor here. If there was a resistor here, okay, in this branch, okay, in this branch over here, then it's not so easy, because then you need to do maybe node analysis and define voltages and so on. Okay, but in our case, there is nothing here, which means that I can effectively split the circuit into 2 halves. Okay, which means that whatever current that I want to find I1 is only an effect based on this 10 volt circuit, a 10 volt source. Okay, because I1 is only flowing through a part of the circuit that is connected only to the left hand side. Okay, so you do not need to actually worry about this right hand part of the circuit. You just need to focus on the left hand part of the circuit. Okay, so if I look at this left hand part of the circuit, okay, so let me redraw it over here. So I have 10 volts. Okay, I have 8 ohm resistor. Okay, and I have 2 resistors in parallel, okay, 20 and 30. So since we know that they are parallel, okay, so again, why they are parallel? Because when current flows, okay, so regardless of which way current flows, okay, let's assume current flows this way, okay, or whichever way. When it comes to this point, it will split into 20 and 30, which means that both of them are parallel. Okay, so 20 parallel with 30 will give me 12 ohm. Okay, so this part of the circuit here will be 12 ohm. All right, so now we have a much simplified circuit. So the current that I want to find I will be 10 over 20, which is 0.5 ampere. Okay, now the thing is, since we know that current flows from the positive to the negative, the current is flowing in this clockwise direction. All right, it's flowing in this clockwise direction through the circuit. Okay, but the label direction, okay, that is already given to us is in the opposite direction. That means we are given I1 to be pointing in this direction. Okay, that means the I1 is actually 0.5 ampere, but is supposed to go in the opposite direction. So the actual value is minus 0.5. Okay, so again, most students get a bit confused with this. Why must I put a minus? Okay, if I did not give you, okay, if the question never give you this, okay, in arrow, okay, and just say find, let's say I 8 ohm. If they just said that, it's find the current through I the 8 ohm resistor. Then you can solve it and you can say that the current through the 8 ohm resistor is 0.5 ampere. Okay, but here what we have done is we have given you a convention. That means we are labeling the current to flow in this direction from left to right. Okay, so it's already been labeled to flow in this direction, left to right. Okay, but upon solving the circuit, we know that the current is actually flowing in the opposite direction, which is right to left. Okay, so since we know it is flowing in the opposite direction, the I1 is actually negative 0.5 ampere because it's supposed to be going in the opposite direction. Okay, so again, similar to the earlier question, okay, on the KVL, KCL, when we came up with the expressions, okay, we follow, okay, the conventions if it is already given in the question, correct, or given in the circuit, whatever direction or whatever polarity is given. If it is not given, then we assume and we can draw. Okay, but it's already given, then when we get an answer, we must relate it back to what is already given. Okay, and then base the answer on that. Okay, that is why in this case, the current, though is 0.5 ampere, because it is labeled in the opposite direction of what is really happening, then we need to put the negative sign there. Okay, so that is question 6. Okay, so let's go on to the next question. Okay, question 7. Find Vxy. That means find the voltage difference between points X and Y. Okay, so this is, I mean, if you want to simplify or look at it a bit simpler way, you can just draw it as 2 parallel branches. All right, this is 3 ohm, this is 5 ohm, and this is 12 ohm, and this is 4 ohm. Okay, so we know that 3 ampere is coming in, and by current divider rule, okay, by current divider rule, we can say that if I want to find the current through this branch, it is the opposite resistance, okay, which is 16 over the total resistance. That means 16 plus 8 multiplied by 3. That's the current divider rule. Okay, so you can use the current divider rule whenever you have 2 branches. Okay, so with that, you know that this will be 2 ampere. Okay, so 2 ampere is flowing there, which means that 1 ampere is flowing here. Okay, 2 ampere flowing there, 1 ampere flowing there. Okay, so that is based on the current divider rule. Now, what is the voltage at X and what's the voltage at Y? Now, we do not know any prior voltage, correct? We do not know what is the voltage at the start over here. Okay, so what we know is whatever is this reference voltage, from this branch, 2 ampere is flowing through the 3 ohm resistor, which means that this voltage drop over here will be 2 multiplied by 3, okay, which would be a minus 6 volts drop. Okay, so this minus 6, okay, why I put as minus 6? Because this is a 6 volt drop from reference to this point over here. So whatever the voltage, I do not know. Okay, but I know that since 2 ampere is flowing through the 3 ohm resistor, that means that with reference to this point, I will get a negative 6 volt drop at point X. Okay, similarly, I can also say that when I look at point Y with reference to this point, it will be minus 1 ampere multiplied by 12, which will be minus 12 volt. So again, I'm taking with reference to the common point, okay, at the branch. So with reference to that point, point X will be 6 volts lower and point Y will be 12 volts lower. All right, so with that, we can say that Vxy, which is Vx minus Vy, will be minus 6 minus 12, which will be 6 volts. Okay, so if I were to use my multimeter and connect to both points X and Y, I should get a reading of 6 volts. Okay, so that is how you solve this. That means you look at the current flowing in both the branches and then look at what is the voltage drop across the resistor, and then from there you can solve. Okay, so I will proceed. Again, if you have anything, you can ask. Okay, so in this question, all right, so again, how to look at it is, we know that the current that flows out of here will split into 120, 120. But after it's split, over at this line over here, there will be some way in which they will join and then they will have to split again. Okay, they have to join and then they have to split again. All right, so if I were to sort of redraw this circuit, okay, I can draw it this way. I can draw it such that initially you have two branches, 120 and 120. Okay, and then after it's split, it will come back and then it will split one more time. And when it split one more time, it is 100 and 150. Okay, so technically what you have here is two resistors in parallel, 120 parallel 120. Okay, it should be 16, and again 100 parallel 150, which should also be 60. Okay, which means that since both the combined resistance is same, that means the voltage drop, okay, from here to here is the same. Okay, so they're both equal, so you get 5 volts here and you get 5 volts here. Okay, and since both 100 and 150 ohm are also parallel, which means you also get the same 5 volts over here. Okay, so yeah, so that's how you do this. All right, so always remember, when the current splits, then we say it's parallel. Okay, then later, of course, it may join back again and then split one more time. All right, like what you see here. Okay, so question 9. Okay, so we will do this question and then we'll take a short break, then we continue. Okay, so for question 9, if VBD is 1 volt, okay, find X. Okay, so let me first again redraw the circuit. So I have X over here, 4, 6. One, 3, 2. Okay, so this is 6 volt. So this is your A, this is your B, this is your C, and this is your D. Okay, so we are given that VBD is 1 volt. So this is 1 volt. Okay, the 6 volt supply, find X. Okay, so the first thing is we can see that both these branches are parallel, correct? Both this branch over here and this branch are both parallel, and they're both parallel to the 6 volt. That means the 6 volts is the same 6 volts that appears across the lower 3 resistors and across the upper 3 resistors. Okay, which means that I can actually calculate the current here, I as 6 over 1 plus 3 plus 2. Okay, it should be 1 ampere. Okay, so that is the first thing. We know that the current is 1 ampere. Now, the next thing is, we know that since the 1 ampere is flowing through this branch, okay, so this is 1 ampere flowing through this branch. So when it flows through the 2 ohm resistor, what happens? When it flows through the 2 ohm resistance, there is a voltage drop. So V equals to IR, which is 1 times 2, which is 2 volt. So the point C is the same. So this C is 6 volt, correct? Because C is connected to the battery. And when I pass through the 2 ohm resistors, there is a 2 volt drop, which means 6 minus 2 means D is effectively 4 volts. Right? D is effectively 4 volts because, okay, it's just like if I were to draw a separate circuit like this, 6 volt, and I say 2, 3, and 1. Okay, and I tell you that the current is 1 ampere means, then you know that I got 2 volts, 3 volts, and 1 volt drop. Okay, so the voltage drop experienced by the 2 ohm resistor will be 2 volts. So from 6 volt, if I drop 2 volts, I'll get 4 volts at point D. Okay, we know that VBD is 1 volt. That means VB with respect to VD is always 1 volt higher. So if VD is 4 volts, VB will be 5 volts. Okay, because VBD is 1 volt. That means VB is always 1 volt higher than VD. Okay, so with that, okay, I can now say that if I look at the branch over here, this branch over here, B is 5 volt and A is ground. So if I want to measure the current through from B to A, this current here will be given as 5 over 6 plus 4. Okay, it should be 0.5 ampere. Okay, it's the same if I were to again redraw this circuit as a separate. Again, they are both parallel branches. So I can redraw this and say this is X, this is 4, and this is 6. Okay, and if I tell you that the point here is 5 volt, and we know that this is ground, this is 0 volt, correct? So with that, I can say that the current here is 5 minus 0 over 4 plus 6, correct? The same thing. Okay, the same thing if I were to try to draw it separately. So now I know that the current flowing through this branch is 5 over 10, which is 0.5 ampere. Okay, so now that I know the current flowing through this branch, I can now finally calculate what is X. So R is R. R is V by I, correct? So what's the voltage difference? So the voltage difference here is, this is 6 volt at the top, at the other end is 5. So it will be 6 minus 5. And what is the current? 0.5 ampere, which will give me 2 ohm. Okay, so that is how you go about solving this. So there are a few steps involved, all right, but the concepts are the same, right? We are still applying the same Ohm's law, KVL or branch current and so on, the same concepts. Okay, but it's just a bit tedious to solve. Okay, so let's take a short 5 minutes break. Okay, so we don't stay at the screen for too long. Okay, so now it's going to be 3. So about 3:05 we'll come back. Okay, now it's 2:58, 2:59. Okay, 3:05, 5 minutes time we'll come back, and then we'll continue with the rest of the questions. Okay, so in the meantime, if you have anything that you want to ask, you can put in the chat first. Okay, then later when we come back in 5 minutes time, I will address those questions. Okay, so I'll see you all back here in a while. Okay, so let's continue. Okay, so the question for so the first question on the circuit analysis techniques. Okay, I think from the time we started this module, all our midterms have always been MCQ based. I mean, not only midterm, both the first and second assessment always MCQ, okay, which means that yeah, I mean, if it does ask you to find some voltage or current or resistor or something, whatever technique you use is fine. Okay, so that would not be an issue. Yeah, unless of course question specifically specifies that, okay, find the voltage at this particular node or whatever, then maybe you want to use node analysis or it could be some other technique as well. Okay, so there's a question on question 6. Okay, so again, why is this considered two separate circuits? Because like I said, whatever current that is flowing here in this branch or in this branch is only going to be effect based on the 10 volt, and whatever current that is flowing here is only going to be based on the 20 volt. Okay, because there is no voltage drop in the middle where both the circuits are connected. Okay, so since there is nothing here that causes a voltage drop between these two circuits that are connected, then you can effectively treat them as two separate circuits. Okay, if there was something there, then it's not so straightforward. Then you need to use either Thevenin's or node voltage or some other technique to go and figure out the current, okay, through the branches. Okay, so again, the way to look at it is you can just draw a loop, okay, to see how the current will be defined in the loop. Okay, so like I said, if I draw a loop here, I can say that the current through this branch is only going to be through the 20 volt and the 3 ohm resistor. Right, because there's no other component within this loop that is going to affect the current flow. Okay, so that is how you can sort of separate out the two circuits. Okay, so let's continue. So question 10, node voltage analysis. Okay. Okay, so in node voltage analysis, like what we have seen in the nodes as well. Okay, basically you can define. You're free to define any number of nodes. Okay, and wherever you like. Okay, but the key thing is always to try to minimize the number of nodes so that you can solve it with lesser number of equations. Okay, so of course, having said that, it's good if your calculator has some features to solve those kind of simultaneous equations easily. Okay, because during the assessment, you're not allowed to use any online resource. Okay, so you're not allowed to, like in the studio, you use some equation solver from some website or whatever, right? But in the actual assessment, again, I'm not very sure. You might, I can't remember whether we allowed it last time or not. Okay, but in case it is not allowed, you may only be able to use your calculator. Okay, so so it's always good to know what your calculator can do. So if your calculator can help you to solve things a lot easier, then you're free to use those features. Okay, so in this case, your voltage here, which is here, is V. All right. So you know this is what you want to find. Okay. So by node voltage analysis, you can always take all the current flowing in to the node or out of the node, okay, to add up to 0. Okay, so again, it's up to you to define. Whichever way you define it is correct, doesn't matter. Okay, so if I were to define it as all the current flowing out of the branch, so I will say that V minus 6, okay, over 0.2 plus V minus 5 over 0.1 plus V minus 4 over 0.05 equals, plus V minus 0 over 10 equals to 0. That means I assume all the current flows out of the node. Okay, then when I factorize it, it will be 1 over 0.2 plus 1 over 0.1 plus 1 over 0.05 equals to 6 over 0.2 plus 5 over 0.1 plus 4 over 0.0. Okay, and then the rest is just maths, correct? So I'll just go to the answer, 4.56 volts. And once you know V, you can calculate the I, correct? Which is 4.56 over 10 ohm, which is 0.456 ampere. Okay, so that is your current, your voltage and your current. Okay, so this is quite straightforward, correct? Like we saw, we can take any node and just write equations based on all the current flowing in or flowing out, and then from there you solve. So in our case, since you declare one node V, then one equation is enough to solve. Okay, then you get your unknown. Okay, so question 11. So the same thing. We want to find how much power is the 6-volt source supplying or consuming. All right. So we need to know how much current is actually flowing in that 6-volt branch. All right. So to do that, again, we have given you the hint, which is use node voltage analysis. So again, the same technique, correct? So if I define this branch or anywhere on this as BL, okay, whichever point doesn't matter, then I can write expression that all the current flowing out will be equal to 0. So the same thing. So the equation will pretty much look the same. BL minus 10 over 1 plus BL minus 8 over 2 plus BL minus 6 over 3 plus BL minus 0 over 4 equals to 0. Okay, then the same thing you factorize out, then you bring over. Okay, eventually the final answer will be 7.68 volts. Okay, once you know VL, you can also know that. Okay, so once you know VL is 7.68 volt, we know that since 7.68 is higher than 6, that means the current is actually flowing into the 6-volt branch. Current is flowing into the 6 volt, this branch over here. Okay, so how much is the current flowing? The current will be, current through the 6-volt branch will be 7.68 minus 6 over 3, which will be 0.56 ampere. Okay, so that is the amount of current flowing into that particular branch over here. Okay, so in this case, if current is flowing in to the positive terminal of a device, then we say it is absorbing power. If current is flowing out of the positive terminal of a device, then you say it is supplying power. Okay, so in this case, current is flowing in to the positive terminal, so it is consuming or absorbing power. So how much power? That is IR, correct? So it will be, VI. So you can say 6 multiplied by 0.56, which should be 3.36 watt. Okay, you know it is flowing in because current will always flow from a higher potential to a lower potential, correct? So in our case, since VL is 7.68 volt, so this point is 7.68, and this is 6. So current is always going to flow into the 6-volt branch. All right, so based on the potential difference. Okay, so again, this idea of current flowing into a source, correct? Again, this is basically what happens when you charge your batteries, correct? When you plug in your charger to a handphone or whatever, you are supplying current into the battery, correct? That means current is flowing into the positive of your battery to charge it up. All right, so that is the idea behind current flowing into a source. Generally, current flowing through a resistor, or in the next studio we'll talk about capacitor or inductor, is more obvious, correct? But when current flows into a source, okay, that is when it is absorbing power. Okay, that means you're charging the battery in a sense. Okay, so let's go on to the next question. Okay, so in this case, we are coming up with a Thevenin's equivalent circuit seen by R5. Okay, so let's so to solve Thevenin equivalent basically means that you want to take any complicated circuit and simplify it to a very simple circuit with a single Thevenin's voltage and Thevenin's resistance. Okay, so let's do Thevenin's resistance first. To do Thevenin's resistance, basically what we need to do is we replace this source R5, okay, with a imaginary battery source. Okay, so again, that is an easy way to do it. And then the other components we short circuit. I mean, the voltage sources we short circuit. Okay, and then we just keep the resistors R1, R2, R4. This is a short circuit. Okay, so that is basically the circuit you will get after you remove the load, which is R5, short the voltage sources, and you imagine there's a imaginary power supply there. Now, if I look at this circuit over here, okay, the first thing that I will usually want to do is I want to redraw it in a way that I can see clearly what is happening. Okay, so you can see that this branch here, this point here is the same as this point. So this is actually the same point. Okay, so I can sort of redraw it one more time just to be a bit more clearer. Okay, that I have a single branch where R1 comes out, R2 comes out, and R4 comes out. Okay, and then all three combine together, okay, which is this part over here, and all go back to the same point over here, which is part of the imaginary battery over here. So if I were to imagine the current flow, where the current comes out here, that current will split into R1, R2, and R4. So as long as current splits into two or more branches, then those branches are considered parallel. Okay, which means that this RTH, Thevenin's resistance, is actually R1 parallel to R2 parallel to R4. Okay, which is effectively 1 parallel with 2 parallel with 1, which will give me 0.4. Okay, so that is how you view the circuit, okay, to solve this Thevenin's resistance. Okay, now the next step is, of course, the Thevenin's voltage. Okay, so to solve Thevenin's voltage, what do we need to do? That means is the open circuit voltage, correct? That means, let me redraw the circuit over here. So I have a 10 volt. R1, R4, R2, I volt. Okay, so the open circuit voltage means this is the voltage VTH, right? There is a voltage between this point and this point over here. Okay, so how can I solve this? Correct. So again, it all depends on how complex the circuit is. All right. Again, in the situation like this where you have supply over here, okay, it's not so easy to just analyze. Correct. So one of the techniques that we know is node analysis. So if I label this as V1, then I can say this will be V1 plus 10. Okay, and then I can create this particular point here as a supernode. And I look at all the currents either flowing out or flowing into this supernode. Okay, so again, this node voltage analysis is quite useful, correct? When you see the circuit is a bit complicated, you're not very sure how to do it, then by declaring nodes, okay, you, especially with the power supply, you know, in the middle, then you declare one end as V, the other end is the V plus the supply amount. Okay, that itself can help you to have a single expression to solve for the unknown voltage. Okay, so with this, I can come up with my expression. Okay, so I can say that, okay, let me write, this is R1 is this 1 ohm, 2 ohm, and 4 ohm, correct? So I can say, if I take this branch over here, it will be V1 plus 10 minus 5 over 2. Okay, then if I take this branch over here, plus V1 plus 10 minus 0 over 4, plus this branch over here, V1 minus 5 over 1 equals to 0. Okay, so I have an expression, okay, based on voltage analysis, and then with that I can solve for V1. If I solve for V1, I'll get the answer as negative 3 volts. Okay, so again, this negative 3 volts, how do I represent it? So this V1, which is this point over here, is actually your VTH. So this V1 is actually your VTH. Okay, now whenever we say we want to take a circuit and convert it to the Terminus equivalent, correct? That means, what am I saying? I want to take this whole complicated circuit and I want to represent it as a VTH, okay, RTH, and that's it. That is my load. Okay, so this is how we draw, correct? We always draw the Terminus equivalent with VTH such that the positive terminal is on top, negative terminal is below, correct? Now, when we have the answer given as negative 3 volt, then what does that mean? That means the voltage is actually in the opposite direction. That means when I want to draw it, again, it will be the opposite direction. That means the voltage source will be this way. Okay, and then your resistance, which is 0.4 ohm, and then you have your load. Okay, again, why is it we are drawing it the opposite way? Okay, because the convention is when I draw my Thevenin's equivalent, is always drawn with the VTH upright. That means the positive is on top and the negative is below. Correct. But since the value that I calculate for VTH is negative, so I draw the supply in the opposite direction. Okay, so it looks like this. Okay, so the positive is below, okay, and the negative is on top. Okay, so again, this is because of the convention of how we define the drawing of the Thevenin circuit. Okay, so let me move ahead first. Okay, Thevenin's equivalent. So it's another example on Thevenin. So let me go ahead to solve for the RTH first. So for RTH, what will happen is we will short this. All right. So when we short this, we short the supply. So A, I have 4 ohm, 2 ohm, I have 6 ohm, and I have 3 ohm. Okay, so like I said, the way to do it is you imagine you have a supply over here. Okay, so when you have quite a few components, all right, and you want to simplify the circuit, you always start from the end and work back to the front. Okay, so that is how you go ahead. So in this case, we know that whatever current comes here will split into here and here. Okay, and whatever current comes here will also split into here and here. So you go to the end of the circuit. So this is the end of the circuit, correct? Because after I pass through this 3 ohm and 6 ohm, I'm going back to my imaginary supply over here. So I start with the end. So this 3 and 6 are parallel. Correct? This 3 and 6 are parallel. So that will give me 2 ohms. Okay, so from here I can simplify and I can have 2 ohm and 2 ohm. Okay, this is 3 parallel 6 will give me 2 ohm. Okay, then I have 4 ohm over here. And this is my supply. Okay, so again, this 2 and 2 will give me 4. Correct, so this will give me 4 and 4. Okay, and eventually 4 and 4 will give me 2. 4 parallel 4 will give me 2. So that is your RTH, your 2 ohms. Okay, so that is how you go about getting the answer. Right, you start with the end of the circuit. So the end of the circuit in this case is the 3 and 6 ohms. So you start with that first. So we know that 3 and 6 are both parallel. So 3 and 6 parallel give me 2, and this 2 and 2 are series. So 2 and 2 series will give me 4, and 4 and 4 parallel will give me 2. Okay, so now that is your final Thevenin resistance. Okay, how about your VTH? So to calculate VTH, we again start from the end and work backwards. Okay, so this is what we want to find, VT. All right, so we know that this is open circuit voltage. So if this open circuit voltage means there is nothing flowing here. All right, that means whatever current flowing through the 2 ohm resistor is the same going to the 4 ohm resistor, which means that 2 and 4 are in series. All right, 2 and 4 are in series, which means I can redraw this circuit into this 3, 6, and 6. This 6 is 2 plus 4. Okay, and then I know that this 6 and 6 are in parallel. Okay, 6 and 6 are in parallel, which means I can redraw it one more time. 3, let me redraw it over here. 3 and 3. Okay, and this 3 is 6 parallel with 6. Okay, so now we have what we want to find is this. We want to find the voltage across the 4 ohm resistor. Okay, which means I need to find the voltage across this whole 6 ohm resistor, which is equivalent to the voltage across this 3 ohm resistor. Okay, so since in our case it is 3 and 3, so we know it is equally split. Correct, 9 volts will equally split, so I'll get 4.5 volts here. Okay, again this is easy because they are both the same resistor. So it is 4.5 volts against this 3 ohm resistor, which means the same 4.5 volt here. All right, so coming back over here, the 4.5 volt is over here, correct? So it's across the 6 ohm resistor and across the 2 and 4 ohm. So if I were to look at the 2 and 4 ohm, basically this is what I have, correct? 4.5 volt, and I have a 2 ohm resistor and a 4 ohm resistor, and the VT is the one that is across the 4 ohm resistor. So it will be a voltage divider rule. Okay, and that will give me 3 volts. Okay, so the final sort of circuit would be VT, which is 3 volt, RT, which is 2 ohm, and this is your load. Okay, any questions on this? Okay, so we can go on to the next one, question 14. Okay, so for question 14, it is similar to the one that we did in our studio. Okay, to find a Thevenin's equivalent. So if you look at the approach to Thevenin's equivalent is we assume a direction, correct, and we draw or look based on an assumption, and we come up with the circuit. Okay, so since let's say I draw it clockwise, then I will assume the current is flowing in this clockwise direction. So the voltage drop here is plus minus here, and this is plus minus here. Okay, so the battery 12 volt is equals to whatever current that is flowing, let's say call it I, multiplied by R2, which is 0.28 ohm, plus I multiplied by 0.15 ohm, plus 12 volt. Okay, now in this case, what you see is both the voltages are the same. So when I bring the 12 over, then 12 minus 12 will become 0, correct? So effectively your current will be 0. Okay, so if your current is 0, okay, if the current is 0, that means there's no current flowing. That means there is no voltage drop across R1 or R2. Okay, so the open circuit voltage, which is Thevenin's voltage, that means if I remove the load over here, and if I see the voltage here, it will just be 12 volt. Okay, so of course this is in the ideal case, correct? That means both the batteries are exactly the same voltage. So if they're exactly the same voltage, there will be no current. Okay, so if you look back at the studio, eventually that is what would happen if you leave the circuit on long enough, correct? Initially there will be some voltage difference and there'll be some current flow, but after some time, when both the voltages are the same, then the current flow will stop, correct? So the effective voltage seen would be whatever the voltage that is left, that is common across the batteries. Okay, so in this case, since both the voltages are already the same from the beginning, then there is no current flow. Okay, which means that the Thevenin's voltage is actually the 12 volt. Okay, how about the RT? So if I want to look at RT, it will be both the sources short circuit, so 0.28, 0.15, okay, and if I were to place the imaginary source here, then whatever current comes out here will split into this branch and this branch. That means they are both parallel. Okay, that means RT is equals to 0.28 parallel with 0.15, which will be 0.098 ohm. Okay, so the final sort of Thevenin's equivalent circuit will be 12 volt, 0.098. Okay, and then the rest is the load. Okay, so that is the final Thevenin's equivalent circuit. Okay, so now in the part A, they say what will happen if the load is 2.5 ohms. So if my load is 2.5 ohms, then the current will be V by R. So this is the Thevenin's voltage, 12 divided by the total resistance. So total resistance is 0.098 plus 2.5, correct? And then you get 4.62 ampere. And the voltage across the load, again, use voltage divider rule, which is 2.5 over the total resistance multiplied by 12. Okay, so you can see that the voltage that you see at the load side is 11.5 volts. Okay, now if I were to change the next is the load voltage higher or lower compared to using just one of the two batteries alone? Okay, if I use just a single battery, that means if I use battery 1 alone, that means if I were to take it like this, 0.28, and then I connect my load. Okay, or if I just use battery 2, then I get 0.15. And do this. Okay, in both cases, you will see that if I calculate the voltage, okay, using the voltage divider rule, the voltage will be always lower compared to if I use two batteries. So when I use two batteries, the VL is always higher. And why it makes sense is because when you have multiple batteries, the multiple resistors in parallel, the effective resistance will always be smaller than the smallest resistance. Correct. So when I have multiple resistors in parallel, the effective resistance will always be smaller than the smallest resistance, which means that when I do an effective voltage divider, the voltage to the load will always be higher. Okay, the voltage to the load will always be higher. So having multiple batteries actually helps to reduce the overall resistance, okay, internally of the battery. Okay, which means that you can deliver a higher load to the higher voltage to the load. Okay, so that is what this question is trying to make us see. Okay, how having multiple batteries actually helps, okay, in delivering a higher voltage to the load. Okay, question 15. Question 15 is more of understanding this thing called maximum power transfer. Okay, so the idea behind it is, okay, when you have a Thevenin's equivalent circuit, okay, you know that your circuit is already simplified to a single voltage and single resistance. Okay, what value of RL would allow the maximum power to be transferred over? Okay, so if I were to look at this from the current perspective, this will be VT over RT plus RL. And the power to the load will be this IL square multiplied by RL, which will be VT over RT plus RL square RL. All right. Now, I think most of you have know the differentiation rule, correct? Which means that if I differentiate the load with respect to the variable, in this case, which is the RL, and let it equal to 0, that is where I can find the maximum. Correct? When I differentiate and let it equal to 0. Okay, so again, this is just to show you how it is derived. Okay, so the sort of derivation is shown here. So this is nothing more than your quotient rule, okay, for differentiation. Okay, so when I apply that rule, okay, and I simplify, okay, eventually what I get is this. Okay, so this is quite significant, that the maximum power is transferred to the load only when the load resistance is equivalent to the Thevenin's resistance. Okay, so again, this is quite important, okay, because when your load resistance does not match the Thevenin's resistance, you may still get some output, but it may not be the optimal output, okay, because the maximum power is not transferred over. Okay, so if you were to plot, okay, the response of the power delivered to the load, okay, with varied load resistance values, you will get a curve that is something like this. Okay, where the point where you see the maximum power, okay, is where the load resistance is equivalent to the Thevenin's resistance. So that is the maximum power that you get. Okay, anything before that, after that, it will always be lower. Okay, again, for now, maybe you will not see the effect of this so much yet. Okay, but when you build your own circuits, okay, and then you may see that how come the power delivered to the load is very low, my LED is not so bright, or motor is not so fast, or something like that, then you may need to come back to the Thevenin's equivalent to see whether the load resistance is matching the Thevenin's resistance. Okay, and then we can calculate to see whether something can be done. Okay. So question 6 is basically leading up from that. So if I were to now that we know this principle, whenever there's a question that says what is the value of RL in order for me to have maximum power, automatically we know that that is, in a sense, a hint that we should find the Thevenin's equivalent circuit. Okay, so to find Thevenin's equivalent circuit, we need to find VT and RT. So to find RT, okay, so maybe I'll go and find RT first over here. So to find RT, you short the source. So I have 2 ohm and I have 6 ohm. And if I place this sort of imaginary supply here, whatever current that flows out here will split into the 2 and 6. That means the RT is basically 2 parallel with 6, which will give me 1.5 ohm. Okay, 2 parallel 6. For VT is the open circuit voltage. So when I look at VT, which is basically over here, so it says open circuit, the current only flows within these 2 branches over here. So I can just draw a simple Kvl loop. Okay, so when I draw a simple Kvl loop, I can see that if the current is flowing in this anti-clockwise direction, so the voltage drop across the 2 ohm resistors will be plus on top, minus below. For the 6 ohm will be plus below, minus on top. Okay. So to know this voltage, I can first find the current. Okay. So the total current in this circuit here, I, is given as 8 over the total resistance. So 2 and 6 are in series, which will be 8 over 8 should be 1 ampere. So when 1 ampere flows in, which means that over here I'll get a 2 volts drop. Okay, which means that the VAB or VT is 2 volts. Okay, if you want to look at it from the other branch, it's also the same thing. If I look at it from this branch, it will be 8 volt here and 6 volt here. So it will be 8 minus 6, which will also be 2 volts. Okay, so both these branches are parallel, which means that the VT is actually 2 volts. All right, so I can draw my Thevenin's equivalent circuit as 2 volts here and 1.5 ohm. Okay, so once we know this, we know that for maximum power to be delivered, RL must also be 1.5 ohm. That is when maximum power is delivered. And how much is this maximum power? So that maximum power to the load is, you can use I square R, or I square R, which will be, so the current will be V by R, which will be 1.5 plus 1.5 multiplied by RL, which will be 1.5. So that will give me 0.671. Okay. So let me proceed on. So these are all the workings. Okay, so question 17 is the same. Okay, to find the maximum power, again, you find the Thevenin's equivalent. Okay, so let's go ahead. So I will always usually find RTH first. Okay, but it's up to you, whichever way you want to do it. Okay, so the first thing is I will short the sources. So I have 1 ohm here. I have another. Okay, let me draw it the same way. You can see. Okay, so 1 ohm here, 2 ohm here. So this is the short circuit, and this is the A and B, and then this is the short, and this is your 4 ohm. All right. So again, if I were to imagine that I put a supply here, when the current flows out over here, from this point, it will split to here and here. So it split to 1 and 2. Okay. When it passes through 2 at this point, okay, it sees that you have a 4 ohm branch and a short circuit branch. Okay, and as I mentioned earlier, it will always take the path of this resistance. So if there's a short circuit, you automatically go to the short circuit, which means that the 4 ohm is no longer part of the circuit in this situation. All right, so whatever current comes out of A splits into 1 and 2 and comes back in again. Okay, which means that the RTH is effectively 1 parallel with 2, which is 0.6670. Okay, so that is your RTH. Now there will be VTH. So to calculate VTH, okay, again, you can use anything, any technique you like. So in this case, since you see a loop over here, you can define or you can draw a loop. Okay, and you can draw or you can write an expression based on the flow and the plus or minus that you have. So you can say that this 12 volt here is equivalent to this current multiplied by the 1 ohm plus the current multiplied by the 2 ohm plus the 6 volt. Okay, again, this is based on you drawing it clockwise. If you draw it anti-clockwise, it's also the same. Okay, then you can go ahead to solve. So 12 minus 6 will be equals to 3i. So I will be equals to 2 ampere. So if I is equals to 2 ampere, you know that the 2 ampere is coming out here. So let me redraw this a bit. Okay, so that is easier for us to see. So this is A, this is B. So on one side, what you have is you have the 1 ohm resistor and you have the 12 volt supply. Okay, on the other side, what you have is you have the 2 ohm resistor and you have the 6 volt supply. Now, in terms of the current flow, okay, like what we saw just now, the current is flowing in this direction. So for the 12 volt, this is the plus and minus. Okay, the voltage for the 1 ohm, the voltage drop is plus here and minus here. Because the current is flowing clockwise. So when the current flows to the 2 ohm resistor, the plus is here, minus is here. and the 6 volt is also plus here and minus here. Okay, and both these branches, okay, the green one and the red one, both of them are both parallel branches. So I can calculate VAB using the left side or the right side. So if I calculate it using the left side, what I get is 12 volt minus IR. So which is current is 2 ampere multiplied by 1. So I will get 10 volts. If I calculate it from the other side, I will get 6 volt plus 2 multiplied by 2, which will be also 10 volt. Okay, again, why is it plus on the right side? Because both the voltage drops are in the same direction. Whereas over here, the 12 volt is in the upward direction, the 1 ohm is in the opposite direction. Okay, so either way, you'll get the same answer. So we know that the voltage across VAB, which is the Terminus voltage, is actually 10 volt. Okay, so once you know that, you can go ahead to finalize the circuit. So you have 10 volt here, which is your VTH. RTH was 0.667 ohm. And then that is your load. Okay, then the rest is the same. In order for my maximum power to deliver, this is the same as your Thevenin's resistance. And the power will be the same way that we calculated just now, which will be I square R. So it will be 10 over 0.667 plus 0.667. This is your I square, and your R is 0.667, which will give me 37.5 watt. Okay. So that is, again, maximum power delivery sort of questions is always the same thing. We are going to look at the Terminus equivalent and then solve from there. Okay, the last question here, question 18. Okay, I think this was one of the midterm questions. Can't remember last semester or one before that. Okay, so for this, find the RT across nodes A and B. So across nodes A and B, okay. So how do you go about doing this? Okay, so let's go ahead to do what we're supposed to do, which is short the supply. So this is your A, this is your B, this is your 1, this is your 3, this is your 2 ohm, and this is your 4 ohm, and you still have one more branch here. So like I said, we imagine that we put a supply here. Now, when the current from this supply comes out, it will split into here and here. Okay. When it splits into here and here, we know that there is a short circuit branch here. Okay. But even though there's a short circuit branch here, it still has no choice but to still go through 3 and 4 to come back and close the circuit. Alright, there's no way it can just go to short circuit and somehow jump back to the battery. Alright, in order for current to flow, there must be a complete path between the positive and negative. So even though it flows through 1 and 2, okay, at this point here and here, it will split. Something will go into this branch, but we do not know what. Okay, but effectively it has to come back by splitting again through the 3 and 4. So the combined current from 1 and 2 again has to split into 3 and 4 before it can go back into the supply. Okay, before it can go back into the supply. That's so because of that, we can say that at this end you have 1 parallel with 2, okay, because it splits into 1 and 2. And when it's coming back, it has to come back by splitting between 3 and 4. So it again has to split between 3 and 4. So the total resistance is 1 parallel with 2, add with 3 parallel with 4. Okay, and that will give me 2.38 ohms. Okay, so that is how we sort of calculate the RT for this. Okay, so yeah, I know there's quite a lot of questions, but again, the idea of the tutorial is to sort of go through more questions to practice and make you more sort of confident in solving these questions. All right. Yeah. So when it's nearer to the midterm and the final assessment, there will be additional practice questions that we release. Okay, to give you more sort of hands-on in solving these circuits. Okay, but again, the question and tutorial is just to reinforce what we have covered in the past few studios. And similarly, when we finish a few more studios, then again we have another tutorial and so on. Okay, so that sort of wraps up everything you wanted to discuss. Yeah, if you have any questions, you can ask me anything you want to discuss. Yeah, so I think I haven't given you all my number. So if you want to ask me any questions, you can usually WhatsApp is the best. Okay, WhatsApp I will usually reply quite quickly. Telegram I'm a bit more. I mean, quite a few other chat groups in Telegram, so somehow I get a bit overloaded there. Okay, so I think if you WhatsApp me, generally I will reply. If it's a lengthy discussion or whatever, then you can send me email. But it's a short clarification or whatever, then you can just WhatsApp me. I will reply. Okay, so I will still stay on the line for anybody who has anything you want to ask. If not, thank you, and I will see you all on Thursday for our next studio. Okay, so there's a question: how does the current flow in each branch? Yeah, so since we know that the calculated value of VL is 7.68, so we can say that for the 6-volt current is flowing in, okay, but here the current will flow out, and here will also flow in here. So that's how you will draw the branches. Okay, so yeah, you're free to log off. Thank you. Yeah, so if any questions, you can stay back and ask. If not, yeah, the slides, the official slides, I think Sing would upload or may already uploaded. This recording and all, I will upload and I will send you all the link later. Okay, so current is flowing out because the voltage of the batteries is higher compared to the node voltage. Okay, so for question 18, why are 3 and 4 ohms parallel? Because whatever current that comes out here, okay, when it splits back and let's say current flows in this branch over here, okay. So what is the current flowing in this branch? We do not know, but what we know is eventually, in order for me to come back to the battery, I need to come back this way. That's the only way back to the negative, which means that the only way I can go back is I must eventually split this current here into both 3 and 4. So since I'm going to split into 3 and 4, then we consider them as parallel. Because there's no other way for the current to flow back into the negative of the terminal. Okay, current that flows out of the terminal eventually has to go back to the negative. That means when the current splits here and here, all right, so it will reach this point and this point, correct? So when it reaches this point and this point, okay, some current may split here and some current will split here. Same thing, some current will split here, some current will split here. Okay, so no matter whatever current that flow into this short circuit branch, for the current to flow back, okay, into the 3 and 4, this current has to go back only through this branch. Okay, now it is not, we cannot say that all the current that flows through 1 flows through 3, because there is this additional branch over here, which means that the current that flows through 1 and 2 will eventually mix together, correct? So how much current from this combined branch 1 and 2 flows into 3 and 4, we do not know. So we can't say that all the current that flows through 1 goes through 3, or all the current that flows through 2 goes through 4. We can only say that if I did not have this branch. So if I did not have this branch, then we can say that 1 and 3 are series, and then 2 and 4 are parallel. Okay, so if I did not have this branch, then it would be 1 plus 3 parallel with 2 plus 4. There is 2 parallel branches. Okay, that is if I do not have this branch. But since I have this branch, which means that I cannot say that all the current from 1 is the same current that flows through 3, because there is another branch over here. Right, there's another branch over here, and there's another branch here, which means that some current will get mixed together. Okay, question 17. Which part you want me to explain? The VTH, is it? Okay, so for the Tamlin's equivalent circuit, okay, so for the RTH, like I said, we short the source, correct, and then we see that the current that flows out here will split into the 1 ohm and 2 ohm resistor, which means that after it splits to the 1 and 2 ohm, at this point, since there is already a short circuit path, the current will take the short circuit path, which means that no current will flow through the 4 ohm resistor. So the only Thevenin's resistors left are 1 and 2 in parallel. Okay, for the VTH, again, this is open circuit voltage. So if you redraw the circuit like this, you can see that basically you are trying to find the voltage across this point and this point. Okay, which means that I can draw a simple KVL loop Okay, draw a simple KVL loop. Okay, and based on the loop, I can define my plus and minus and then write the expression, which is what I have done here. That means I assume clockwise, so 12 volt is positive. So as this is the direction of my loop is on one side, and since I'm assuming the current is flowing in a clockwise direction, the 1 ohm, 2 ohm, and 6 volts are all in the opposite direction of my current flow. So they are on the other side of the equation. Okay, so with that, I can solve for I. Okay, once I solve for I know the current that is flowing in this loop. Okay, then I can calculate the voltage either on the left-hand side branch or the right-hand side branch. All right. If I take the left-hand side branch, it is the source. Okay, it's a 12 volt. But for the resistor, the voltage drop is in the opposite direction. Okay, because for 12 volt, the plus is on top, minus is below. For the 1 ohm, the plus is below, minus is on top. So it's in the opposite direction. So I subtract. Okay. For the right hand side, they are both in the same direction. So I add up. Okay. So whichever way you get, whichever branch you choose, you get the same answer. You get 10 volts as the VTH. Okay, so I think no other questions, so I will end the session here. If anything else, don't worry, we can still discuss any other doubts you have during the class studios as well. Okay, so thank you everybody. I'll see you all on Thursday. Okay, bye.